This video is on what is the probability of a tie in Georgia. Okay, so let's look at the counts in Georgia. Joe Biden has 2,463,706. Ah, damn it, I just typed in the numbers into Mathematica and they just changed. Well, okay, they're going to be close enough. The analysis still applies. My numbers are just slightly different because they just updated them, whatever. Donald Trump has 2,454,710 votes. So I'm going to show you an analysis of calculating what is the probability of an exact tie in Georgia. Okay, let me show you how that works. Okay, here's the model we're going to use. Suppose we flipped this Donald Trump coin 5 million times. There's approximately 5 million voters in Georgia. I'm going to give you the exact number, but it's close enough to 5 million. And let's say there's a 50-50 chance that the voter will either vote for Trump or Biden. So we're going to flip the coin 5 million times and calculate what is the probability of an exact tie. Let me show you how that works. So first, suppose we just have two coins. What is the probability of an exact tie? If we flip two coins, there's 4 total outcomes, 2 of which are exact ties. We can see these 2 in the center. This one is a tie. By tie, I mean the same number of heads and tails. Same number of heads and tails. So the probability of a tie is the total number of ties divided by the total number of outcomes, which is a half in the case of 2 coins. Okay, now let's move to 4 coins. Again, the probability of a tie is the number of ties divided by the total number of outcomes. Well, the total number of outcomes for 4 coins is 2 to the 4th, which is 16. That's in the denominator. And in the numerator is the total number of ties. If you go through all these 16 different possibilities and count the number of ties, you'll see there are 6. And there's also a formula for that. We have n coins, and we want a tie, so that means there's n over 2 that are heads and n over 2 that are tails. So to count that number of ties, it's n, choose n over 2. And the total number of outcomes is 2 to the n. Now if you use Stirling's approximation for n factorial, this complicated math thing, because carrying out this calculation involves factorial, it's going to involve a factorial of 5 million factorial, which is 5 million times 499,999, all the way down, keep multiplying all the numbers down to 1. So it's some crazy kind of thing. So we don't want to do that. We want to use Stirling's approximation. And if you do that, you get this, which is very interesting how this scales. So this is for any number of coins. If I have n coins, the probability of getting the exactly the same number of heads and tails is the square root of 2 over pi times n. So the scaling is interesting. Basically scales as 1 over the square root of n, which if you had asked me before I thought about this, I didn't know that's how it scaled. This is actually, the function 1 over the square root of n, doesn't go to 0 particularly quickly. Like, in particular, it's not like an exponential thing. It's in the realm of possibility. So now here we are in Mathematica. That's how many votes Biden has. This is how many votes Trump has. And the total number of votes is about 4.9 million, roughly 5 million. So this is the exact formula. This is dividing by 2 to the n, the total number of possibilities, and n choose n over 2 is the number that are ties. So it turns out it's this number, 0.00035, whatever, which is approximately 1 over 2,779. So when they say, what is the probability of there being a tie in Georgia under this model? By the way, no one's saying that it's a particularly accurate model of a coin flip for in Georgia. It turns out in Georgia it's fairly close, so that's why I'm using this coin flip model. But in other states it's completely different. They're heavily going in one way or the other. So here, and here's the approximation. and it looks like, you know, to 6 significant digits, this Stirling's approximation is exactly correct. Mathematica can do this gigantic factorial, you know, where it's doing 5 million factorial, so somehow it's able to do that, and that matches exactly our approximation. So the thing to remember is this scaling. The exact, if you flip a coin n times and want to get an exact tie, that scales like 1 over the square root of n. So there you go. Now, I just made a table here just out of curiosity. Here's the exact column. This column is the exact column, and this is the approximate column. So the approximation gets better as the number of coin flips n gets larger. So like we counted when I was showing the Donald Trump coin, for 2 coins, it's a 50% chance of getting a tie, and this approximation says that. For 4 coins, we calculated this. What did we say? Like, for 4 coins, we calculated this to be 3/8. That's the exact number, and the approximation tells us this. But, you know, once we start getting large, like here's about 1 million. Whoops. I don't know. Here's 1 million. It's already accurate to 6 digits. So the scaling is like 1 over the square root of n. But then I said, okay, what if we make the binomial distribution for this coin flip to look at the variance and standard deviation? Like how close are we to what we would expect with this kind of model? So the mean is just the total number of votes divided by 2. The variance, so this is a property of the binomial distribution. The variance is just the total divided by 4. And the standard deviation is the square root of the variance. So here the standard deviation is about 1100. So let's see. Biden minus the mean is about 3700. So Biden's ahead. So the mean is saying like if it was an exact tie, the exact same number of votes for Trump and Biden. So Biden is ahead of the mean by about 3,800, say. So if you ask how many standard deviations is that? So I was wondering, because the question, I was wondering like, oh, is there some kind of fraud? Is it too close or something like that? But no, it's not too close. And it's even pointing out that this is kind of this coin flip model is kind of a crazy model. It's saying Biden is 3.4 standard deviations ahead. So that's way ahead of the coin flip model. But there's nothing to say that the coin flip model is an accurate thing. So now we can create a normal distribution on what the binomial distribution should go from 0 to 5 million with a mean at 2.5 million. But on this scale, we don't even see it because the standard, remember, the width of the Gaussian is roughly proportional to the standard deviation. So on a scale of 5 million, you know, the standard deviation of 1100 doesn't even really show up. So we got to zoom in. So here's like zooming way in. It's really highly peaked. And here's when I zoom in only 4 standard deviations away, we can see. So Biden was like 3.4 standard deviations ahead. So in this, so there's no, if everybody was voting by a coin flip, we're definitely in the fat part of the distribution. Like there's no, I was thinking it was going to be too close to say, oh wow, this is statistically too close, but it's saying no, most of it is not too close. So I guess the thing that I learned also is this: the variance is just the total over 4 for the binomial distribution. And then because n is so large, this thing is converging to a normal distribution. So instead of using a binomial distribution with a parameter of 5 million, I just switched to a normal distribution. So all that, long story short, the probability of a tie in Georgia is 1 over 2,779. So in the quantum mechanics many worlds theory, one of those worlds there will be an exact tie in Georgia. Why not yours? The other thing is, I really like this quantum mechanics many worlds theory where, you know, in some universe, if it's possible, then it will happen in some of these weird universes. So I'm just wondering, like, why can't I be in the universe where like everything good happens to me? Some universes like that where I'm the king and everybody, you know, throws cash at my feet and everything like that. And if it's possible, it can happen. So some universe it's like that. So you just gotta find that universe and live in there where everything good happens to you. And thank you very much. I also have this other video on Donald Trump eliminating the $1 bill. So it's kind of an interesting thing with Diophantine equations. If you eliminated the $1 bill, what prices, and you had the other dollar, you had a $2 bill, a $5 bill, a $10 bill, $20 bill, etc. Would there be any prices that you couldn't buy because they eliminated the $1 bill? So you can watch that video. Bye.